Okay, welcome. This is the exam 2 answer key. So the first question asks us to draw the ZR stereoisomer of this compound. We have a double bond. We want to draw that in a Z configuration, a Z geometry. And we have a chiral center that we want to draw in an R configuration. By the way, there's a missing hydrogen here. I posted an announcement during the exam indicating that you should add an additional hydrogen, of course, if you missed that. So to see the Z geometry, this carbon here has a chlorine and a hydrogen. We can put the chlorine here, you can put it down, and then so the hydrogen would go here. And this vinyl carbon has a hydrogen and the rest of the molecule. For the Z geometry, the two hydrogens are going to be on the same side, right? And then you have the rest of the molecule, CH2. And then we have the chiral center. All right. So let's put the represent the tetrahedral carbon with two bonds in the plane and one forward and one back. Let's put the hydrogen pointing away. That's the way we're supposed to look at the molecule to assign configuration. And to do R, chlorine is the highest priority group and oxygen of the OH is second highest priority. Of course, the carbon would be third and the hydrogen, the low priority group. So if we orient the molecule like that, you see you go 1, 2, 3, that's clockwise. That's an R configuration, okay? So that's a structure for the ZR stereoisomer of this particular molecule, okay? There's several of the ways to represent it, but they need to, include these features, okay? Okay, so I hope that's helpful. I'm going to erase this and go on to the next question. The next question asks us to draw the most stable chair form of the following sugar. And so let's do that. I'm going to draw the chair. I'll put the oxygen here. You can put it anywhere. Okay, that's the chair. And, normally we start up here, but that's a lone pair there. And there's a lone pair here. You don't have to put those in. But we have axial up, so then we'd have axial down, axial up, axial down, axial up, axial down. And since this axial is down, we have equatorial up, equatorial down, equatorial up, equatorial down, equatorial up, right? So starting from the oxygen, we move clockwise. The OH is up. This one's up, so that would be in an equatorial position, right? And then the next one, the OH is down. Okay, that's the down group is also equatorial. And then we go to the third carbon, we have another down OH, and the third carbon, the down OH is axial, right? See, that's the down group. And then the fourth carbon, the OH is down again, and the fourth carbon, the down group is equatorial. And then the last carbon, the CH2OH group is up. And as you can see, that is going to be equatorial up. Okay. So that's the structure. We have 1, 2, 3, 4 groups equatorial, and one of the OHs. This one is in an axial position, and that's the most stable structure. Okay. So as you go around the ring, up or down, just you have to look at whether the up group is axial or equatorial, and the down group is axial and equatorial on the particular carbon that you are working on. Okay, so I hope that's helpful. I'm going to erase this and go on to the next question. Okay. So the next question is, what's the name of this compound? So we're going to number the chain from left to right. That gives the bromine substituent a 2. If you numbered it from right to left, you would not get a substituent numbering would be higher. So that's a 7-carbon chain. That's heptane. Right, we have a bromine at the 2 position, so that's a 2-bromo. Then at the 4 and 5 position, we have methyl groups. So 2-bromo, 4,5 that's dimethyl, sorry, dimethyl heptane. And that's not complete. You have a chiral center here. And if you assign configuration, you'd find out that's S. So the full name for this is S2-bromo 4,5-dimethyl heptane. Okay. I hope that makes sense. I'm going to erase this now, and we will go on to the next question. So we're going to draw a bond line structure or a Fisher projection for the following Newman. Okay. So we have, how many carbons do we have? Well, we have one carbon and then 2 carbons. And then the one behind the circle is 3 and this methyl is 4, right? So we have 1, 2, 3, 4 carbon chain, right? And we know looking down the bond this way, and this would be the front carbon here and the one behind the circle, that's the back carbon there. So the groups off to the right, the bromine, are the ones in a wedge position. And then the hydrogen going to the left is going away from us. You can leave that out if you want. And then in the back, the bromine is off to the left. So that's going back. Oops, that's the bromine. And then the hydrogen is off to the right. So that's the one that's coming forward, right? So that's the bond line structure from the Newman. And if you assign configuration, this is S, and this one's R, all right? Okay, and so there's a couple of ways of looking at this. And let's look at it through the Newman. If you rotate the front group 180 degrees, so let's keep the back group fixed. So we have the Br to the left, the hydrogen to the right, and the methyl down. If we rotate the front group 180 degrees, this bromine will go 60, 120. This bromine will be eclipsing that bromine. This hydrogen, 60, 120, 180 will be eclipsing that hydrogen. And the methyl will flip all the way over 60, 120, 180, and will be eclipsing this methyl, right? And so if you look at that structure, there's actually a plane of symmetry that bisects the carbon, the front carbon and the back carbon bond. You can't see it here because you have to, rotate around the CC bond to see the plane of symmetry. But there's a plane of symmetry. Here's the front carbon, the back carbon is behind the circle. There's a plane of symmetry that bisects that bond. So you have a bromine on either side of the plane, you have a hydrogen on both opposite sides of the plane, and you have 2 methyls. So even though this compound has 2 chiral carbons, it's achiral. This is the plane of symmetry, and it's an example of an achiral meso compound. Okay. So I hope that is helpful, and we're going to erase this and go on to the next question. So consider the following reaction. Gave you a hint to look at all this stuff is covered in textbook section 6.8 to 6.11. So identify the elementary process and draw curved arrows to show the movement of electrons in the reaction. Okay, so you see what's happening here? The Br-Br bond is breaking, correct? So we're going to have to take the electrons in that bond and move it onto the bromine. See, the bromine picked up an electron. The bromine picked up an electron. I'm going to erase this, make this a little bigger. So this bond broke and the bromine picked up the electron. That's why it's become negative. And then you formed a CBr bond, right? And the pi bond here, this pi bond broke. So this pi bond broke and formed a bond to the bromine. Okay. Yeah. The pi bond broke. So this carbon here is losing a bond that's going to develop a positive charge. Okay. So those are the two curved arrows. Okay, notice what happens. CBr bond formed, pi bond broke, BR bond broke. And that's a nucleophilic attack, right? The electrons in the pi bond are forming, attacking the bromine, all right? That's a nucleophilic attack. There's no rearrangement. You could also include a loss of a leaving group. I took nucleophilic attack as a correct answer, but the Br is leaving the Br molecule. So you can also point out there was a loss of a leaving group, okay? So that's the first one. The second one, a lot of people didn't get this right. So let's look what's happening here. You have a hydrogen here, and you're getting this is a carbocation rearrangement. That's true. It's a rearrangement, but what's moving is not the methyl group, it's the hydrogen. This is secondary carbocation, and the H with the electrons are moving. It's a little, it looks like the methyl moved, but if the H with the electrons move, then the positive charge ends up on the carbon with the methyl, right? See that? Yeah, let me erase that and redraw it so you can see it more clearly. So you have this CH bond, and the H with the electrons are moving. That leaves this carbon here with only 6 electrons in the positive charge, okay? So this is a hydride shift. Rearrangement is fine, but it's a result of a hydride shift that converts a secondary carbocation into a tertiary. I rotated the molecule a little bit, so it kind of gave you an illusion that the methyl moved. But if the methyl moved, the positive charge would be on a secondary carbon. You wouldn't go from secondary to tertiary. Okay, hope that makes sense. And then in the last step, this is just, again, a nucleophilic attack. There's the arrow. You're forming a CCl bond. And so this is another example of nucleophilic attack, okay? So these are the elementary processes that we talked about in class, and that are covered with many examples in the textbook, all right? I hope that makes sense. And of course, with any of this stuff, we can let me know if you have any questions. I'm going to erase this and move on to the next question, question 6. So here is to consider a 3-step energy diagram. So let's draw the diagram, where the first step is slower than the second. So we need and then it says the second is much slower than the third, right? So here's the second, and it's going to be much slower than the third. So let me complete this. All right. So the first step is slower than the first. So this barrier is much bigger than this barrier. That makes the first step slower. And the second step is much slower than the third. So this barrier for the second step, you see, is much bigger, making it much slower than the barrier for the third. Okay, so something like that. It doesn't have to look exactly like that, but the relative barriers should reflect the fact that the first barrier is bigger than the second, and the second one is considerably bigger than the third. The equilibrium constant is near 1. That means the free energy of the reactants and products are the same, right? So delta G would be approximately 0. That gives an equilibrium constant of 1. These points here are reaction intermediates. right? Those are species that are formed and then consumed. And these structures at the top of the energy hills are the transition states, for the individual steps, okay? And then if you want to point out, these are the activation energies for the individual steps. That's worth pointing out too, okay? So I gave partial credit depending on how much of the diagram you described, okay? So I hope that makes sense. I'm going to clear this and go on to the next question. Okay, so I'm going to have to look at the table of bond association energies real quick. Sorry, should have had that ready. All right, so let's look what happened. The bond association energy of a pi bond in ethane is 62. So what we want to do is, what bonds are broken on the reactant side? Well, a pi bond broke, right? You go from the pi bond broke, you go from a CC double bond to a CC single bond in the products. So that's 62 kilojoules per mole, right? That's given as 62. And then an HCl bond breaks, and an HCl bond is 431, right? Kilojoules per mole. So if we add those up, that's 3 and 9, it's 493 kilojoules per mole to break the bonds, right? Now, what bonds are formed? So a lot of people didn't do this right. So you see, we form a new CCl bond, right? But we also form a new CH bond, right? Look, the CH2 became a CH3, so there's a new CH bond formed, and of course we formed the CCl bond. So the CH bond is 410. If you look that up, that's 410 kilojoules per mole. And the CCl bond is 339. That's to a primary carbon. So if you add that up, you add all that up, let me do that. Sorry, I can do that manually. 9, 4, 749. When bonds are formed, energy is released, right? So that energy is released. So we have 493 kilojoules per mole to break the bonds in the reactants. And we're getting out 749 from the formation of the new CH and new CCl bond. And so what we want to do is take 493 and subtract 749. And what we get is 493 minus 749 minus 256. Minus 256 kilojoules per mole. That's the delta H for this reaction. It's exothermic, strongly exothermic. Okay. In terms of the entropy change, you have two molecules on the left and one on the right. So you've lost the degree of freedom of motion, right? You had two molecules that are free to move around. And now on the right side, you only have one. So the delta S for the reaction is going to be negative. We have a negative delta H and a negative delta S. What can we say about the expected change in free energy? Well, delta G is delta H minus T delta S, right? This is negative. We have a negative delta S, but we have a minus sign here. So the minus times the minus gives you a positive term here, right? So whether delta G goes up or down is going to depend on the temperature. If temperature is low, then the entropy term is going to be small and delta G will be less than 0 and the reaction will be spontaneous. If T is very high, then the dominant term is going to be the entropy term. And that's positive, so delta G will be positive and the reaction will not be favorable. So based on that, you can see that these addition reactions to alkenes are normally normally run under low temperature conditions, okay? So I hope that's helpful, and I will clear this and go on to question 8, all right? Okay, so it says the naproxen, S-naproxen, is the active ingredient in Aleve. It has a specific rotation of plus 66. And we get a commercial preparation results in a mixture that is 97% enantiomeric excess. What is the percentage of each enantiomer in the preparation? So here's how I would do it. That's how I did it. 97% enantiomeric excess means you have 97 plus X. Now, X is the amount of the minor component. So we have 97% more of the S-naproxen than we have of the R. And then we have the amount of the R-naproxen. That's equal to 100%, right? So this is the amount of the R-naproxen. And the enantiomeric excess means, this is the R, means we have 97% more of the S, right? So this whole term here is the S, the amount of S naproxen, right? So the S plus the R has to equal to 100. So if you add this up, you have 97 plus 2X equals 100. 2X is equal to 3, 100 minus 97. X is 1.5. So that's 1.5%. That's the amount of the R naproxen. And then 97 plus X is the amount of the S naproxen. So 97 plus 1.5 is 98.5% of the S naproxen is in the mixture, okay? So that's one way of doing it. Okay. I hope that makes sense. And I'm going to clear this and go on to the last question. All right. Okay, so here, this one confused a lot of people. How many stereoisomers exist for the following structure? So we have 2 substituents, right? So we can have a cis isomer, right? And we can have a trans isomer, right? Where one's up and one's down, right? Okay. So both of these molecules have a plane of symmetry. And look, there's a plane bisecting the bromine. I see that? The plane of symmetry. There's also a plane of symmetry here. Right? Okay. And so both of these molecules are achiral. Both of these molecules are achiral. They have a plane of symmetry. So you just have 2 stereoisomers, not 4. And you have a cis stereoisomer and you have a trans stereoisomer, okay? I gave partial credit here. I try to give partial credit where I possibly could, all right? So I hope that's helpful. That concludes the exam 2 review session.